Hello everyone, this is Fred Dimock, the Manager of Process Technology at BTU International. This presentation is entitled Making Case for Continuous Furnaces, or What Do I Really Need to Know? At BTU, we talk about going back to basics numerous times, so we're going to talk about that basically throughout this presentation. The question that we put on the table first is, what's the difference between a batch and a continuous furnace? At BTU, we often talk about going back to basics, so what we're going to do is use that approach through much of this presentations. Okay, so we're going to start with discussing the differences between batch and continuous furnaces. Let's first talk about batch furnaces, okay? Basically, you put the product in the furnace, you close the door, you run a recipe or a thermal program, then open the door when it's cool and remove the product. They have a number of different names for them, depending upon the industry you're in. But basically, they have programmable recipes, they have a lot of flexibility, and sometimes they can actually be inexpensive. On the other hand, continuous furnaces are a bit different. You continually load the product into the furnace. It usually goes on a belt, or sometimes it can be a pusher. It goes into a tunnel and persistently comes out the other end. And when I say persistently, that means if you're not there, it's still going to come out the other end. They have a number of different names for that, conveyors, belts, layers. Again, it all depends upon the industry involved in. Even things like glass tanks and steel furnaces, you put product in, it melts, and it comes out as liquid. They have programmable recipes, but they have limited flexibility, and sometimes they're relatively expensive. But the flexibility, within range, you can actually have some flexibility in continuous furnaces, just not as large a range as you would have if you're running a batch furnace. So the question really arises, when does it make sense to go to a continuous furnace? Both of those can be designed for various atmospheres like hydrogen, nitrogen, air, argon, foaming gas, vacuum, and mixtures. Batch furnaces are very good for long thermal cycles. Like I said, they have high flexibility in that thermal cycle. Not necessarily in the atmospheres, although sometimes they can. Continuous furnaces are best for stable, well-designed, understood processes. They have high productivity or high volume, and they're really good in repeatable thermal cycles. When you run a batch furnace, you're not always 100% sure it followed the same recipe each time. Continuous furnaces have ease of operation because they're running and just put product in there. And there are times when you have high volumes that floor space really is less when you're using a continuous furnace. So the next question is, what do you need to know before purchasing a continuous furnace? Obviously the thermal profile or the process window, and maybe both. You need to know peak temperature, the hold times, the ramp rates up and down, intermediate hold times, and time over intermediate temperature. The atmosphere is important because it makes a difference as to how the furnace is designed. Air, hydrogen, nitrogen, mixtures of hydrogen and nitrogen. In some cases, it's important to know the dew point in the furnace and even the oxygen levels, especially if you're running the nitrogen or hydrogen. You need to know the product size, the height, the width, and the length, the weight, the heat capacity, or is it even put in carriers of some sort. It's also important to know what you need, the throughput you need in that furnace. You need a number of parts per hour, per day, per week, or how many shifts it's on. So let's focus on continuous furnaces. There are a number of subgroups in continuous furnaces. There are things like walking beams and pushes and belt furnaces. Even within that group, it's important to understand that there are differences in furnaces that are designed to run in air, explosive gas, or even non-explosive gas. Those are very critical things to know. In convection furnaces, it can be air, nitrogen, even vacuum. In vacuum, we'll talk a bit more about that later. And then obviously there are the specialty furnaces for very, very special processes. Okay, we're going to talk about the individual types of furnaces now. We're going to start with the big boys. Those are the walking beam furnaces. They've very high throughput. High weight can go through those. Very high temperatures. They can be hydrogen and nitrogen mostly. Once in a while you see a walking beam in air, but those are the big boys of continuous furnaces. There are also pushes, and they are a little bit lower in temperature, 1800 degrees C, and the weight's just slightly less. Walking beam uses a reciprocating beam that moves product forward. It lifts it and moves it forward. Where pushers have basically a train that goes through the furnace where the pusher is pushing pallet against pallet to go through. The big problem with pushers is when you get very high weight, they tend to be hard to push, and if the pallets aren't taken care of well, you can actually end up with crash with those, where things buckle up. And when that happens, it's not very good. But usually pushers are designed so that you do not have those kinds of issues. The next furnace we talk about are the belt furnaces, and specifically in this case, we're talking about air. They're called conveyors or belt furnaces. They tend to be a maximum temperature of maybe 1150 degrees C, and the weight limit is basically because of the belt is around 15 pounds per square foot. They're going to have metal alloy or ceramic belts, although most people are using metal alloy belts in those furnaces. The ceramics tend to be a little brittle, but the good thing is they have precision temperature. Now that's the air furnace. The next we'll talk about are the belt furnaces of non-explosive gas. They're different than the air furnace because generally they have a metal muffle or a seal case to entrap the gases in there to stop the air from getting into those furnaces. They tend to be argon, nitrogen, or less than 4% hydrogen, which generally is called foaming gas, although some people call foaming gas higher levels of hydrogen than that. They have atmosphere and temperature control along with dew point and O2 levels in the furnace. They have the same basic weight capacity as the air furnace at 15 pounds per square foot, and temperature capabilities are still the same thing. It's about 1150 degrees C. The next one of the belt furnaces is explosive gas. These are the fun machines. These are the ones that do an awful lot of work. And because of the explosive gas, they have to have special burn-off stacks, etc., so that we don't have issues with explosions and that, because hydrogen mixed with air does not do very well. It therefore has burn-off ports with flames and safety interlocks so the machine runs safely. It tends to be hydrogen greater than 4%. We talk about the foaming gas again. I've had some people say that, oh, we use foaming gas, and you find out that they're up at 15 or 20% hydrogen, and that means you really need to go to explosive gas furnace with all the safety interlock. Again, they have metal muffles. Sometimes they'll have seal cases, but we're not real comfortable with seal cases in these. We really like the metal muffles when this work. Again, they have atmosphere and temperature control, dew point, and sometimes O2 control, where somebody needs a very, very low oxygen level, let's say it's down to 1 or 2 parts per million. You can do that in these furnaces quite easily. The next are convection furnaces. They can be done with either air or nitrogen, and basically heating with hot gas. It's like your convection oven at home, except it's got a belt that goes through it, and they tend to be a little bit warmer. We'll go to 400 degrees C is the general peak temperature of these, although there are a few that you can see that run maybe 425. It's used basically for solder reflow or epoxy curing when they're down at 100 degrees C. They have multiple heating lengths. They both usually have top and bottom heat and an internal cooler. They're really a workhorse for that lower temperature area. And convection works significantly better than radiation when you're trying to do precision control at those lower temperatures. This is a typical convection reflow oven. The top one is nitrogen. The bottom one is air. When I'm able to do animation, it's a little easier to explain this, but we'll try here. See, if you look at the top oven, the nitrogen oven, you'll see that the entrance of the oven has a lip fan exhaust in the curtain area. The curtain is to isolate the room atmosphere from the nitrogen atmosphere that's inside. At the exit you have basically the same thing, a curtain and a lip fan exhaust. Nitrogen ovens have like I say, the heating zones and the cooling zones, and then usually they have a flux management system, because what you want to be able to do is pull any of the flux that may be in the oven, in the atmosphere of the oven, take it out, scrub it out, and then return that clean nitrogen to the oven itself. On an air oven, you don't care about returning the air to the oven. What you basically do is we eliminate the curtain at the front. We put a lip vent, the exhaust right at the front edge without the curtain. And then what we do on the exit is move the lip vent to between the heated zones and the cooler, because we want to stop any of the flux from moving down in the cooler and condensing there. You'll see on the nitrogen oven I have a green little square around that. We're going to talk about what one of those plenums really look like. Okay, so this is a typical reflow oven heated zone. The top plenum, there's actually one on the bottom that does exactly the same thing, that pushes the heat to it. If this was done with animation, it would be a bit easier to point to the individual items. But let's start at the top left with the nitrogen inlet. Across the top, you see the blower motor. If we drop down a little bit, you see that the blower motor does this blower wheel, and that's what develops the pressure in the chamber. The blower wheel is like a scroll fan. You kind of look like something you put a chipmunk in and have them run around, but it's a lot faster than that. What happens is that scroll fan spins, it pushes the gas across the heater to heat the gas and develops the pressure in the chamber. What the pressure then does is goes through small orifice holes, and it pushes that hot gas impingement down on the board itself. Okay. Then there's a gas return that goes back up the side, so you don't have to reheat the gas each of the times. This is basically the top plenum from a reflow oven. Okay, I mentioned earlier that we're going to talk about some continuous ovens that actually had vacuum in it. There is a convection oven with inline vacuum. This isn't really brand new to have inline vacuum ovens. When I worked in the automotive industry, we actually used continuous vacuum furnaces to flash aluminum on the insides of the reflectors you use in automotive headlighting, although those were very complicated machines and didn't quite go to the kind of temperatures we're talking about here. Those industries, we just wanted to pull a vacuum and then flash aluminum to get it on the surface. The reason we're doing inline vacuum on convection ovens is that on some of the components they're putting in under hood or automotive, in hood on automotive areas, the military and some medical devices, they want to put more power into those. And part of that is to be able to get the heat out of the chip. That means that thermal pads have to be without voids. And that's really what this is about in this. Okay, vacuum levels, you can get down to 1 torr or so with that. So basically what they do is they take a standard reflow oven, they're mostly nitrogen, and what you do is place a vacuum chamber between the last heated zone and the cooling zone. Then you have this automated transfer in and out. So it does interrupt the process during that cycle, but it seems to be working very, very well. This is a typical part of the vacuum process that we see. I pulled one of these things out just to explain what happens in the vacuum chamber. You basically have a pump down, and the rate at which it pumps down is critical. If you go down too fast, you get splatter of the solder, and you get chips that actually turn over. You go down to the vacuum level, the torr level that we get. This one, I think, was down at about 20 torr. Hold time, number of seconds, and then a refill, so the return to room temperature. So that's really what goes on. That time, the total time for that in the vacuum chamber might be 30 or 40 seconds at the most. I mentioned specialty furnaces. There are a number of those that they're designed for different kinds of applications. There's like live bottoms. It looks like a flatbed rail car that travels through a hot tunnel. They're basically air. They can do thousands of pounds. They have very long thermocouples. I think mainly they're used in the brick industry. There are rotary, there are rotating tube furnaces where they have products that's like sand and the tube's at an angle, and you control the throughput of that by controlling the angle and the speed of it, the speed of the rotational speed. Then, of course, there's the glass tanks and steel furnaces that do molten materials. I'm not going to cover much more about those things, but they are things that are continuous furnaces. Okay, so we'll talk about how we get things hot, heating technology, if you would. Basically, there are two methods. There are a few others also, but I'm going to talk about the two major methods. One is the gas, the flame, or electric. Now, I'm not super familiar with the flame. Very familiar with electric heating. And there are people that specialize just in flames and adjusting in flames and controlling it. So I'm going to talk about the electric side. There's obviously convection heating, like we mentioned before when we talked about the reflow ovens. There's things like molybdenum, silicon carbide rods. There's refractory metal rods, mesh, wire, ribbon. Those are things like moly and tungsten. And then there's this fully enclosed ceramic heaters. They call it FEC. Basically, most of the stuff we use is the fully enclosed heater because it protects the heater's surface, and they tend to work. They tend to work quite well for us. Insulation in furnaces can be things like brick, high-performance board, fiber blanket. Some of the things you can use heat shields. They're called cold wall. They usually moly or tungsten, and even graphite and carbon. The issue is when you get to graphite and carbon, you have to make sure the O2 levels are very low. Otherwise, they just disintegrate. There's technology to separate the internal atmospheres of the furnace from the room. Things like purge boxes. I didn't quite have the ability to pull a picture of one of those. This COVID thing has limited the ability to pull some pictures out. We have things like gas curtains. This is the gas curtain in the belt furnace. Basically the same philosophy goes on when you're talking about convection ovens. And then on some of the hydrogen furnaces, you'll actually have flame curtains. We're actually burning the hydrogen at the end that is helping to stop the air and oxygen from moving into the furnace. Those are ones where you actually have, instead of having the stacks in the gas curtains at the ends, like I showed you earlier, those are the ones we actually use this flame curtain at the front of the furnace. The next is technology to separate the furnace atmosphere from the room. There are things like purge boxes, or sometimes called double door airlocks. Unfortunately, I wasn't able to get pictures of this, because of what's going on with COVID. And really, air column air boxes is really not the correct thing. You might call them atmosphere exchange boxes. So they work somewhat like clean room pass-through boxes. We fill a box with hydrogen and nitrogen before opening the internal door to the furnace, so you're not putting air within that furnace. There are gas curtains for separation from the outside to the inside, and they usually have stacks of some sort within the furnace to help control the airflow. Like we did with the Venturi, like with the Venturi that I mentioned earlier. They use it for binder removal and for hydrogen burn-off stacks. Some hydrogen furnaces use flame curtains that act as a barrier to stop oxygen from entering the furnace and hydrogen from getting into the room. The next is the technology to separate the furnace atmosphere from the room atmosphere. There are things like purge boxes, double door airlocks. I didn't have a picture of that. The COVID kind of got in the way of me being able to get good pictures to describe that. And actually calling them double door airlock is probably not the correct thing to say. They're atmosphere exchange boxes. It's like a clean room pass-through box. We have two doors, and you put material in there before you open in the box, close the outside door, and then you open the inside door before you move them through. What happens on furnaces, you fill the box with the hydrogen or the nitrogen before opening the internal door, so you're not putting air into the furnace. You're not mixing the atmospheres between the room and the furnace. The next are gas curtains. That's also used for separating furnace atmosphere from the internal atmosphere. They usually, furnaces that have gas curtains on, usually have stacks that are built into the furnace out of the chamber itself, and they usually have venturis in the stacks to help control gas flow and help with binder removal in the furnace. I'll talk a little bit more about Venturi principle later. If it's a hydrogen furnace, those usually have burn-off stacks where you actually ignite the hydrogen at the entrance of the stack or the exit of the stack as the gas comes out. Some hydrogen furnaces have flame curtains that act as a barrier to stop oxygen from entering the oven or the furnace, and also stop the hydrogen itself from getting out into the room. You can also design into the furnaces things like heat barriers and shadow walls to help you with rapid changes in the process temperature. This is basically heat barrier. You can see this, it's kind of hard to see in these pictures, but this is a barrier that can drop down to actually give you a little bit of isolation. It helps you to have more rapid changes in the process temperature, less crosstalk between the zones, if you would. Another tool that we have is gas barriers. They allow us to isolate or even exclude gases from certain areas of the oven. They have the ability to get very, very low ppm capability to drive the oxygen level way, way down. A very high purity hydrogen atmospheres in some furnaces, and you need the controlled exhaust to make these work. We have a furnace that actually has nitrogen curtains on the end and hydrogen in the center, and we're able to approach 96% hydrogen in the middle of the furnace. And that, some processes that's very important for. Others, you're happy enough to get into the 65 or 70 or maybe even 80% hydrogen in the oven. But there are some that require that very, very high purity hydrogen, again up into the 96% area. We use a principle sometimes called Venturi and Venturi exhaust to help remove gas from the furnace and control the direction that gas goes in the furnace. They have things that call, sometimes they have removable stacks. Sometimes we actually put sparges in, which got added gas that can be heated or non-heated. And this is to help control what goes on in the O2 levels in the furnace. And sometimes you need to pull a binder out, for example, in an area you don't want to contaminate the furnace. You put one of these in. We actually had a furnace at one point in time, easily for us to put another one together, that was used for copper end termination, where we needed to run, maybe 10 or 15 ppm of oxygen for the binder burnout section. And we used a lot of sparges, and we added some gas in there to keep that mixed up. And then what we did is, following just after that, we did it without gas barriers, but we were able to run down to less than 2 parts per million during the sintering section when we actually raised the temperature. That very unique machine. It was a lot of fun to run. We have a quick discussion on Venturi operating principle. I think most people are aware of that. You put high velocity gas through a very small orifice, and it entraps and pulls a lot of gas along with it. It was developed by a guy named Giovanni Venturi, and that's where you get about 8 to 15 times the input. So if you put 2 liters per minute through 2 liters per minute through the Venturi tube, you can pull anywhere from 8 to 10 times, 8 to 15 times the amount of gas through that tube. And we use that fairly often to get the control of which direction we want gas to flow, because generally what you want to do is make sure you have the cleanest gas at the highest temperature within the furnace, because that's where you're doing the major amount of work. We can also use the Venturi principle to help us in accelerating cooling. For example, these are two examples. The one with cross eductors. They're on the left. The one on the left is cross eductors. We'll pull out of one area of the furnace. We'll push the gas through and return it to the other. It's kind of going across. There's one on the left and one on the right. This is in the cooling section. Then we also do parallel cooling. This allows us to shorten the cooling section of the furnace. In many cases, it means that people can fit it in their building, the furnace in their building, and still get things that are cool coming out of the end of the furnace. Another place that we can use Venturi principle is in cooling inductors. That's basically for accelerated cooling. We do essentially pass gas through that small orifice that's inside a tube, and the outside of that tube is it has a water jacket on it that cools the gas and then returns it to the furnace. We can do it either in cross inductors or in parallel inductors. Both of those work. Depends upon the particular product and the particular what we're trying to do at that point in time. These accelerated cooling actually allows us to shorten the cooling section of the furnace. That in turn allows people to possibly fit it in a building they might otherwise not fit it in. So we go back to the question, when should I get a belt furnace? Now we know what options can be put on that, and there are a number of other options that I didn't discuss. It's an economic issue, okay? It's when you have higher volume and you have a need for process repeatability, and you really need to be able to clearly describe the process so the features that we've talked about can be put in the correct places in the furnace. It doesn't do any good if you want a smooth, easy ramp rate and you suddenly put a gas curtain in place, and it doesn't always work. Unless you want to turn the gas curtain off. But it really need to be able to describe the process so the features can be put in the right place of the furnace. One of the questions that come up on a regular basis when you're talking about continuous furnaces is, how do you set it up for or do verification of thermal profiling? To do that correctly, you really need to measure the temperature of the part as it goes through the process. So the question really comes down to, how do you get these product profiles? Now, there's low temperature and high temperature profiling, but in both cases they require a temperature sensor and a data acquisition device. Really, it's thermocouples and a thermal process profiler. So the question becomes, how do you tame these profiles, or these product profiles? Well, there's a slight difference between low temperature and high temperature profiling. They both require a temperature sensor and a data acquisition device. Okay, that's a thermocouple and a thermal process profiler. So we talked about thermocouples, or that temperature sensor. And the question people ask is, what is a thermocouple? What does it really do? Well, this guy named Tom Seebeck, way years ago, 1821, discovered that when two dissimilar metals were joined together, they produce a voltage, like a little battery. The properties of that voltage that are useful to us as process people are it varies with temperature and it's repeatable. The American National Standard Institute has established designation and published voltage tables with different combinations of metals, and they've designated those metals as things like type T, J, E, K, RSB. And there are others that are universally used but don't have official status, such as things as Platinel and Type N. Things get a little complicated as we start talking about what the thermocouples are and which ones we're going to get. There are two different grades of thermocouple wire. One is standard limits and the other is special limits. Well, basically the difference is that the accuracy of a special limit thermocouple is about half, or it's twice as accurate as something that's a standard limit. Now, we tend to use type K thermocouples in the surface mount industry. If we're going to high temperatures, we tend to like to use things like type Rs. But type K is relatively inexpensive. But the whole issue is you need to be able to manage that error, the error that you see. For example, type K, you see it's the standard limits are plus or minus 2.2 degrees, or 0.75% of the reading. If we get up to 850 degrees, you can only be accurate within about 6.5 degrees. It's half of that if you go to special limits. If you make a chart showing the error, and we call it the error cone, you can see what happens with type K. Below 300 degrees C, the area is about plus or minus 2.2, or the special limit says 1.1. But as you get above that 300 degrees C, what happens is the error cones begin to open up. So that's why you see at 850 degrees C, the plus or minus 6.4. Now that's lot-to-lot differences, not variation within a lot, and that's something to be well aware of. On the last slide, I mentioned something called about accuracy. That means that we really need to talk about repeatability and accuracy. Repeatability is the ability to hit the same place each time. Accuracy is the ability to hit the target. A TC, for example, gives an output of 98 degrees C while in boiling water, which really should be 100 C, is said to be accuracy within 2 degrees. If 10 readings for that TC vary from like 97.8 to 98.3, it's repeatable within a half a degree. Repeatability and accuracy. They are slightly different. But there is a road to get to accuracy. Okay, and to get accuracy, what we need to use is certified TCs. Okay, they have an additional cost, usually $75 to $100 for the first temperature and $25 to $30 for each additional point. A lot depends upon where you get them from. The certification documents at the offset at the measured temperature, but it really doesn't address repeatability. Another issue you can run into is thermocouple aging. And this is with type K thermocouples. We were running a project where we were attempting to get plus or minus 1 degree C across the 25-inch wide belt through the peak temperature. Okay, and we were having some issues, so we finally took brand new thermocouples, 6 of them, and ran them down to see the difference, all right next to each other, very close to each other. We found that they were within about 0.5 degrees C of each other on run number 1. Then what we did is held one back, the number 1 TC, the control one, and ran the other 5 of them down through the furnace on multiple runs. After we got done with that, we said, let's see how much they may have moved from the number 1 TC. So we put them all back together again on run number 10. And what we found is those 5 thermocouples were now 2.5 degrees C apart, and they had moved 3.5 degrees C from the original TC. So that's an issue that you can have with repeatability. Now this happened in air. Later, we ran some more studies of doing the type K TCs down in about 225 degrees C. We saw very little change at the temperature. And then we also ran them in hydrogen up at 850 degrees C, and we didn't see very much change at all in hydrogen. So this really had to be an oxidation of those thermocouple joints. So far, we've talked about the thermocouples, but what about these thermal process profilers, or data acquisition devices? Well, I remember previously I talked about low temperature and high temperature. Well, with low temperature profiling, generally below 350, 400 degrees C, you can put a data logger through the furnace with thermal shields, and they will not overheat the profiler. After all, you don't want to melt the solder that's in the profiler. Now, if it's a short cycle, yes, you can do that. If it's a long cycle, you're going to be sitting up there, more than just a few minutes. The thermal shields really won't withstand that. Okay. In the high temperature profiling, what people basically do is use a long trailing wires. They're connected to a data logger that stays outside the furnace. I mean, when we were doing the studies on the that I just previously showed you at 850 degrees C, those were all trailing wire thermocouples. So here's a quick review of what we've covered today. We talked about batch furnaces, programmable recipes, great flexibility. Sometimes they're inexpensive, and they're good for long thermal cycles. Continuous furnaces, again, programmable recipes. They aren't as flexible as a batch furnace would be. Sometimes they can be expensive. They have stable and repeatable processes, and they're good for very large volumes. Things you need to know. Well, it's good to know the process window, the temperature, and the process thermal cycle you need to go through. The atmosphere is important to know. Throughput, yes, absolutely, in the product size. Okay, I want to thank you for listening. This is, again, Fred Dimock, the Manager of Process Technology at BTU International. If you have any questions, you can give us a call. Actually, it's best to contact me through email because things are a little bit busy and been hectic during these periods of time of COVID. But I want to thank you again and have a good day.